Hello? Can you see my screen?
Yeah.
Okay, so next week I'm going to give this 15-minute presentation in the FRB 2020 online conference. It was scheduled in Thailand, but now canceled and moved it online due to the COVID-19. Okay, so my talk is about using FRB as a probe of the intergalactic medium. So, this is work that I have been collaborating with these collaborators, as you can see my cursor, which I highlight two young researchers, Charlie Walker, who was my co-supervisor student in Manchester and now working in Max Planck Institute for Radio Astronomy. And the other is my postdoc, ex-postdoc Anthony Waters, that he has been working on doing forecast, and plus a few other senior people. Right, so FRB is actually a phenomenon of this very energetic, sorry, I forgot to record. Okay, FRB is this very interesting energetic event that happened at basically a quite distant universe, and we detected it with multi-frequency radio telescope, basically, and you can see a typical dispersion showing here in the upper plot. So because of the signal going through the plasma, whether it is around the host galaxy or whether it is around intergalactic medium, the low frequency part will have a delay respect to the higher frequency part. And therefore the time delay would be related to the frequency difference, square frequency difference showing here in the equations, and multiplied by the dm, which we call dispersion measurement. So in fact, that dm is a total amount of dispersion we will see for two given frequency channel, which is related to the line of sight integral of the electron density, or we can call plasma electron density along the line of sight. So this integration 0 to L would be integrated from observers redshift 0, basically our own telescope on the ground, all the way up to the host galaxy. So therefore, this would receive a handful of contribution from different components. And because this whole thing was first discovered by Duncan Lorimer, a professor in West Virginia University, so this event also called Lorimer burst. Right. So what are the contribution to the DM? And the DM, certainly we are here. This is our radio telescope on the ground, such as Meerkat or the Future Hyrax. So we certainly cannot escape from our Milky Way. So therefore, we receive a contribution from Milky Way plasma. And there's a large contribution from the intergalactic medium. So we call it DM IGM, subscript IGM, which tells us about cosmological information. And the other part is a very important, non-negligible part is the host galaxy contribution to the DM, which is not well known, which depends on host galaxy type, inclination, FRB location, and progenitor environment. So it depends on a number of factors. But these three things adding up is a total DM. The question is, if we want to use DM, we want to use FRB to probe the intergalactic medium or probe the host galaxy plasma physics or progenitor scenario, we need to decompose the DM into basically DM IGM, DM host, and DM Milky Way. So Milky Way part is quite well known. We have pulsar data that can, on different angle that within the Milky Way, so we can use that to build a model for the Milky Way plasma model, plasma distribution. But DM, IGM, and also the host galaxy would be relatively less well known, right? So we want to decompose this extragalactic component of the DM, right? And in particular, getting information on of the DM, IGM is particularly interesting because that will tell us a lot of information on what baryons are really is. So this diagram, everyone knows this diagram, this pie chart showing you the percentage of atoms, dark matter, and dark energy, and which shows the atom is 4.6%. And where does this 4.6% number get from? We get it from marrying the angular power spectrum of the CMB. So left-hand side is, lower left-hand side is the Planck CMB map, and we measure the data. We feed the data with the prediction of the CMB temperature angular power spectrum. So we feed that, we vary that parameters, and then feed as a posterior likelihood and get the number from the likelihood. So therefore, we can treat that 4.6% as a model parameter or the mean baryon fraction rather than counting the number, counting the baryon itself. And certainly there's no way to count dark matter and no way to count the dark energy. So we only got this from as a mean value. So not really by counting the baryons, right? But if we really count baryons, we see a offset. That is famous missing baryon problem. So the real counting of baryons would not recover 4.6%, but rather cover 0.46%. So only 10%, only 10% of this 4.6% we know is nature, and also we know is location, or let's say distribution. But 90% of the 4.6% we know is nature. They are baryons, but we don't know where they are. So that's why it's called missing baryon problems. A numerical simulation shows that this is Sen and Ostraker early hydro simulation, but later being updated by a few others to show that most of the missing baryons are actually in the warm-hot intergalactic medium that are pretty dominant at lower redshift. And X-ray, but this is hard to be measured by X-ray because X-ray would be, X-ray flux would be related to the directly proportional to the NE square. So if you have a dropping profile from the cluster center, then the square of it would be even sharper, and therefore X-ray would be only able to measure the very central peak of the baryons. But FRB is a unique probe because FRB directly equals to the integral of the NE over the line of sight. So therefore, whatever model that NE is, you can just measure it, and there's no square effect to only allow you to locate the peak of the cluster. But this would be basically, sorry, the FRB DM would only be would also be related to the filament and others DM. Okay. So we want DM IGM. So we need to remove DM host galaxies. And how can we do this? And certainly future HIRAX would have the long baseline radio interferometers that can be able to reconstruct the local image of the host galaxies and possibly isolate them from the total extragalactic IGM, extragalactic DM. Okay, but now we don't have that tool. The question is, can we still do this? Okay. On the other hand, localization is relatively demanding because it needs long baseline interferometry with a variety of configurations and require optical follow-up to determine the host galaxies. And you still need a model to compute the host contribution, different orientations, and so on. And recently, there's a ASCAP paper published in Nature that's showing how did they do this. But now, for majority of the FRB, we don't know what is the host galaxy, but can we still somehow decompose that from the total DM of extragalactic? So this is a paper that I've been doing with Charlie Walker and Renee, and of doing this, and Tony later on did some forecasts of constraining diffuse gas with FRB. Okay, let's see where we stand. So this is a total. Can you see my cursor? My cursor is gone. Anyway, so you can see the DM observed that is equal to DM Milky Way and plus DM extragalactic, where the extragalactic are IGM plus host. And so I want to know what is the true redshift given the extragalactic DM, right? So I want to know the probability of true redshift, even though I don't know where the host galaxy is. I want to calculate this term in the later in the next equation, given the DM extragalactic. So by Bayesian theorem, that is equal to the probability of the DM extragalactic given the host galaxy redshift, or let's say source redshift, and times the probability of the source redshift divided by a normalization factor, which is the probability of the extragalactic DM. And so PZS is the probability of the source redshift is the FRB redshift distribution. Left-hand side is the probability of DM extragalactic given the source redshift. That is equal to the convolution of the probability of the DM IGM with the probability of DM host given the source redshift. Right. So what we need to do is to do the LSS modeling for probability of DM of IGM given the source redshift, and also do some host galaxy modeling, giving the to give me the probability of DM host given the source redshift, and also multiply by FRB redshift distribution. So we need these three factors at least to compute this function and really infer the source redshift, even though I don't localize the source galaxy. All right, so in this study, we show such attempt and basically compute this whole process and getting the final answer. So for each of the steps I'm presenting now, how can we do it? So for FRB source redshift, we use a E-large distribution, which is basically follow the GRB source redshift distribution. And we assume that this very energetic burst event would actually coming from a similar astrophysical source. So we assume that they are similar. And also we try a flat redshift distribution, and we find eventually that these two doesn't really matter too much. What about the probability of the DM IGM given ZS? So we use various models here. One is a halo model used in McQueen 2014 about the giving a distant galaxy, what is the dispersion of the IGM and also its distribution, which tells us the scatter of this value. And also we use Gaussian approximation, and also we compute the cosmological simulations. As you can see, for redshift equals to unity host galaxies, these are not quite far away, even though the shape vary a bit, but not quite far away from each other. Okay, now the nasty thing comes out. What is the probability of the host galaxy given a source redshift? We don't know what it is at all, right? The host galaxy could be a elliptical galaxy, could be a spiral galaxy, could be could be a lot of different variety of morphologies of these galaxies, and it could also orientate in different place and give us different orientation. So what can we do? Okay, we just consider them all. So what we did is we model the elliptical galaxies, and also we model the spiral galaxies. So the elliptical galaxy model is actually what is being used in literature. So which is, you can think about our Milky Way like a pretty flat disk where the stellar components are just within the disk, and above, in perpendicular direction to the disk, there will be an exponential fall off. And spiral galaxies, we use this beta model to compute the electron densities. And the other important thing is about the probability distribution of FRB within the galaxy, where the FRB is. If we don't know anything, then we don't know anything. But here, basically, we assume that the progenitor should follow the spatial distribution of young stellar populations, such as OB stars or neutron stars. So we model them as the OB stars or young pulsars or old pulsars or the millisecond pulsars. So those are the different scenarios that we modeled. And here I show you a few diagrams showing you what is the probability of DM of the host for different stellar populations. And on the right-hand side, right upper plot, I show you the different age value, which is the, let's say, the displacement of the FRB that in the direction perpendicular to the to the disk, spiral galaxy disk. On the lower panel, I show you these two plots showing you the RE and H, which are also the displacement with respect to the center of the elliptical galaxies. As you can see that certainly if the FRB closer to the center, closer to the bulge of all stars, then the dispersion, it will receive a high value of dispersion value. Whereas if it's more further away of it, then the DM will be relatively drop. It will be, probability will be closer to the center. Okay, then we put them all together. Can you see my upper equation? Look like my bar is blocking it. Can you see my upper equation?
Yeah, I can see it.
Okay, so if I put them all together, I got this plot, which is the left-hand side is probability of ZS given the extragalactic DM value, and what is the inferred source redshift, right? So the solid line is the probability of ZS given the extragalactic DM, and the dashed line is the probability of the ZS given the DM IGM. So you can see that if I have a DM equals to 500, it would almost tell me the source redshift is about 0.5. But there is a variation. There is a, let's say, a dispersion. And that, I can call that, that variance is due to the IGM variance plus the host galaxy variance. And certainly this variance will be broadened if the DM will become bigger. And actually that variance, when you can see the likelihood become broader, the broadening effect is mostly due to the IgM contribution instead of the host galaxy contribution. But on the other hand, you can also see when you compare the solid line with dashed line, so the dashed line is slightly moved towards a slightly higher redshift, and that is due to certainly if you neglect the host galaxy DM and only and regard that 500 solely due to the IgM, you will get a slightly higher redshift. And this difference between the solid and dashed line, the difference between the probability of ZS given the assumption of DM extragalactic or the assumption of IgM will shrink when you go to higher redshift, because certainly for higher redshift FRB, the host galaxy contribution is downweighted by a factor of 1/z. On the right-hand side, this is a known redshift FRB of 121102. That is the repeater FRB that measured by my collaborator Laura Splitter. You can see that the spectroscopy Z is 0.193, which is a dashed line, actually the little dashed line over here. But from our model, we can predict the probability of ZS, which is shown in these two curves, that assuming different FRB source redshift distribution, the flat prior between 0 and 6 and the elong distribution follow from the GRB doesn't really matter quite a lot, but it gives a distribution. It looks like that our model prefers a slightly higher value of ZS than the spectroscopic one. That is probably due to the scatter of the host galaxy. Okay, and so therefore in our work, what we did is for those unknown host galaxy, for a given DM, we can compute a table that give you the FRB and the inferred source galaxy redshift given the model A, B, C, D, E. Those A, B, C, D, E are details. I don't have time, but those are the different galaxy models that we assume for the host galaxy. So if we know optically, for instance, from the HIC camera or other follow-up, maybe picture-wise, LSAT in the future, that we know any of these host galaxies, even if we know a bit information, we should be able to pick up one of these models and therefore pinning down the information more precisely. And the second part of this is that once we know that host galaxy redshift, we should be able to use that to, am I passing my time? I passed my time now, so I need to shrink down my talk. Okay, basically we can use that to probe the diffuse gas fraction, which is basically calculating the FD, as you can see here, that affecting my extragalactic DM, that is related to the basically the integral of this, and that FD is the diffuse gas, which is not the barons already made into stars and galaxies, and not the barons which are in the interstellar medium. So I just quickly go through this. So we generated 10 to the 3 number of samples, aim for future Hyrax detection rate in the year of the total FRB numbers, and we can basically plot their probability of DM over this, and we constrain the value of the diffuse gas fractions. So here we assume a model of evolution, as you can see. Let's just see the lower right plot. You can see that we can constrain that evolution of the diffuse gas in a quite precise manner in about for 1,000 FRB, which is achievable with Hyrax and time in the future 1 year measurement. For the future probe of IgM, by using FRB, we should think about how we combine that with the Shenyayer-Zerdovich map, which is measured from Planck, so that we can decompose that DM with different morphologies of the local structures and therefore infer about the baron content in the filament and even in the void, which is relatively lower compared to the halos. But those are very interesting targets to probe. Summary, most of the FRBs are not localized, and so we do need a good model for deconstructing DM, IgM, and DM hosts from the total extragalactic component. We build such a model by incorporating Gaussian density function of larger structure, elliptical galaxy and spiral galaxy electron densities and stellar population of different galaxies to calculate PDM hosts. And this is the most nasty part, but we have done so. So if we have any ancillary information of the host galaxy, we can plug those information into this model, connect that information, and therefore we should be able to give a more precise computation of this term. Then we can use Bayesian theorem to infer the source galaxy redshift, given the extragalactic DM component. And the results show that this largely depends on the host galaxy model, but inferred redshift are obtainable and relatively inconsistent across these different models. We further forecast that 1,000 localized FRB with a diffuse gas fraction can be quite accurately determined, including its redshift evolution. So our future will be towards relating the DM measurement of the IgM electron density with SA effect to infer the baryon distribution. Thank you.
Thank you, Yin-Zhe. Does anyone have questions? Okay, Matt has a question.
Great question on, you showed some cosmological constraints or projections. I think it was quite quick, so I've kind of missed is that combining with other data or?
Yeah, so these I think these combine with Planck data to fix the omega matter and other parameters, geometric factors. Yeah, omega matter and H. Yeah.
Okay, all right.